A study looked at the relationship between low birth weight and IQ. A random selection of 17 low birth weight children had an average IQ of 95.5 points with a standard deviation of 16. A random selection of 19 normal birth weight children had an average IQ of 104.9 points with a standard deviation of 14.2. Use a 10% significance level to test the claim that the two groups of children have the same average IQ, assume equal variances. So I've underlined this phrase, to test the claim, which is going to indicate to us that we have to do a hypothesis test for this problem. And then I've looked here at this phrase that the two groups of children have the same average IQ. So we want to test the claim that the two groups of children have the same average IQ. That's going to help us get our initial claim, right? And then finally, we have a detail here that's important to us in the problem. It says assume equal variances. They're referring to the population variances. They want us to assume equal variances for this problem. Okay, so what I want to do next is to actually look at the claim and try to express that in symbols, right? Okay, so when I read this phrase here, to test the claim that two groups of children have the same average IQ, they're basically saying the two means are equal to one another. So all we have to do is find a convenient set of notation to label them. So since this problem deals with low birth weight children and normal birth weight children, I'm going to go ahead and put L and N here as my subscripts. So I'm saying the mean for low birth weight is the same IQ for the mean for normal, right? They have the same average IQ. So that's the claim. Let's now compare or come up with our competing pair, of hypotheses, HO and HA. So look at the claim and identify the symbol that's being used. If it's an equal sign, or if it has an equal sign in it, it means the claim is the same as the null hypothesis HO. So in this case, I know the claim and HO are the same. Okay, now at that point, HA has to express the opposite viewpoint, which in this case will be not equal to. Okay, so there it is. Now, at this point, once you have that, the next step is going to be to go ahead and record the data for the problem. So let's go ahead and list all the data that's given in the problem. Let's do it under two titles, low birth weight and normal birth weight, right? And so I'm going to express the N for both groups, right? I'll want to know the sample mean for both groups. And I'll want to know a standard deviation or variance, depending on what they've given us in the problem. And then, of course, I'll have a significance level for these problems as well. So let's talk about the N in the problem. What are the N's? So this is a random selection of 17, right? 17 low birth weight children. They left out the word children there, but it's okay. 17 low birth weight children had an average IQ of 95.5. So we have 17 low birth weight children. The average for that group was 95.5 with a standard deviation of 16. So we say that the S here is 16. Then a random selection of 19 normal birth weight children, right? Had an average IQ of 104.9, right, with a standard deviation of 14.2. And they say here that the significance level is 10%, so 0.10. That's our significance level, 10% significance level. Okay, at that point, once we have all the data, we got to do the test statistic formula now, right? So in order to calculate the test stat, we should observe that the sample sizes are small, and then go ahead and notice that the test stat formula will be a T, test statistic, right? Now, we're going to set up on the top X bar for low birth weight minus X bar for the normal birth weight children. That'll be the first part of it. And then we're going to have a square root for the bottom part. The square root for the bottom part will consist of SP squared over N1 plus SP squared over N2. Now, SP squared refers to the pooled sample variance. So we're using the pooled sample variance because they tell us that we want to assume equal variances. Whenever that's given to us, we have to assume that we're going to use this SP squared value. So that has to be calculated. Let's take the time to calculate it right now so we have it for use in the formula. So SP squared is just a weighted average of the two variances they give us. Now, they gave us standard deviation, so we'll have to square those to turn them into variances. But here's the formula, essentially. We take the degrees of freedom for the first group. So we're going to do 16, in other words, right? The degrees of freedom is just n minus 1 times the standard deviation here squared. That's going to be 16 quantities squared. Then we're going to add that to the degrees of freedom for the second group, which in this case will be 18, times the standard deviation for that group squared. Of course, if we were given the variance, we wouldn't need to square these, but we're given standard deviation, so they must be squared, just like this notation shows squaring. And in the bottom, we just add together those two degrees of freedom, so 16 plus 18, and that gives us the formula for SP squared. Now our next step is to actually calculate that. So let's grab the calculator here and work this out and see what it gives us. Okay, so what we're going to have is 16 times 16 squared plus 18 times 14.2 squared. And when we're done, we're going to divide that answer, which is 7,725.52. We're going to divide that by the sum 16 plus 18. And when we're finished, we get the answer 227.22. So 227.22. Now that goes on and on after that, so I'm just going to put ... on the paper, but I'm actually going to store that value in my calculator for now as a variable, and we'll come back and use that in the formula next. Okay, so to use it then, what we're going to do is take that answer and plug it into this formula for the test statistic, right? So remember, this is the value that we got for SP squared, right? That's that value. We're going to use that now into our formula. So the X bar for the lower birth weight children is going to be 95.5 minus the X bar for the normal weight children, which will be 104.9. And that will all be in the numerator. And then divide that by this quantity, SP squared, which we have here. That's 227.22 ... right? Plus 227.22 ... And both of these are going to be divided by their respective sample sizes. So in this case, it'll be 17, and for the other one, it'll be 19. Okay, so once we fill that in, we can now work it out, right? Okay, so we'll do, in the top parenthesis, 95.5 minus 104.9. Close that parenthesis up, and then hit divide by the square root of. And now once we have that, we can do 227.22 divided by 17 plus 227.22 divided by 19. Close up the parentheses, hit enter, and we end up with that solution. Now, I just want to demonstrate that the answer here is negative 1.8679, so on and so forth. Now, in that case, I didn't go ahead and give the full answer for the SP squared. I kind of stopped there at the 0.22. I want to demonstrate how the answer will be different if I actually plugged in the full value. And the way I'm going to do that is, remember, I stored that in my calculator as X. So I'm going to delete some of these values. I'm going to go ahead and just put in the X instead. So I'm going to do X divided by 17. The X, remember, is the full value without any rounding, right? X divided by 19. And if I do that, I get the answer negative 1.86789. So the answer is almost identical, right? So it doesn't make much of a difference as long as you include enough decimal places to make sure that the answer isn't going to be too affected by it. So just to illustrate that you don't have to be too religious about putting decimal places in. Just give enough to be safe. 2 or 3 is usually good enough. If you want to be safe, you can go up to 4 in some cases. But in this case, we end up with the answer negative 1.8. And if you're going to go to 2 decimal places, we can call it negative 1.87, right? Okay, so there it is. That's our test statistic, right? Now, with that test stat, we want to take that and compare it against a critical value, right? So we have the test stat. We want to now put it on the bell curve and see where it lands with respect to the critical value. So let's draw our bell curve. And we're going to look at the HA next to determine what kind of test we're dealing with, left-tailed, right-tailed, or two-tailed. The fact that it's not equal to, it tells me that we're dealing with a two-tailed test, right? We always look at HA, it tells us two-tailed test in this case because the not equal to sign. All right, it's a t value that we're working with, so we're going to be looking for a critical value for here and here, 2 critical values in fact, right? 1 positive, 1 negative, and that's going to tell us where the reject region begins, right? If it lands in here, we reject. If it lands in here, we do not reject, right? So do not reject HO if we're in here, reject HO if you're in here, or reject HO if you're in here. Question is, where does this guy land? To figure that out, we have to go to our table and get our critical value. So what we're looking for is the critical value, which is going to be located here. And that critical value is going to be a t. it's going to be an alpha split into two tails here. So the alpha is 10%, but we're going to be chopping it up into two tails. So this little point will be alpha t.05 because half of the alpha will be in each tail. And then we're going to have degrees of freedom. And for this guy, the degrees of freedom is simply this plus this minus 2. So we're going to have 17 plus 19 minus 2. Or of course, 34 will be the final answer because it'll end up being essentially 17 plus 17, which is the same as 34. Okay, so let's go to the chart, the t-table. Let's look up in the 0.05 column 34 degrees of freedom, and let's find our critical value. Okay, so we're looking at 0.05 with 34 degrees of freedom. All right, so let's move this down a little bit so we can see that. There's 34 degrees of freedom. We get 1.691. Okay, so from our table, we found the answer 1.691 for our critical value, 1.691, and negative 1.691. Okay, so now comparing those critical values to our test statistic, we see that our test stat, negative 1.87, is over here, negative 1.87. Would land here in the area that we would designate as rejecting HO. So that's going to be our initial conclusion. We're going to reject HO, and therefore support HA. Now, depending on what our claim was, we'll say either that we reject the claim or we support the claim. Now we have to see which one our claim is. When we look at our claim, we realize that the claim is the same as HO. So in that case, I'm going to go ahead and say that our wording should correspond to this statement because our claim is HO. So since our claim is the same as HO, we're going to say that we reject the claim, right? So we're going to say the sample data allows us to reject the claim. The sample data allows us to reject the claim. Reject the claim. And of course, the claim here is that the two means or the two groups have the same mean IQ. And what we're basically concluding here is that low birth weight children do not have the same mean as normal birth weight children. And based on our data, it seems like if they are different, then it would be that the normal birth weight children have a higher IQ on average.